Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. And this is our second video for Module 2. We will cover the Section 3, the Process Control Block, and Section 4, the Operations on Processes. So we're going to actually provide a detailed information about the Process Control Block, the PCB, which was introduced in the previous section. Okay, let's start the section 2.3, the process control block, the PCB. Now, the process control block is the instantiation of a process, which means that once a process is created, then the PCB will be created as well. Now, upon the creation, the operating system assigns a process a unique number, a unique ID. Now, this ID P, it could be a pointer to the PCB structure or an index to an array of PCB. So the PCB is going to be implemented in, different ways. Okay, so we're going to talk about this a little bit later. Now, the specific implementation and the contents of a PCB varies, between different operating systems. So, which particular in this PCB structure, which items should be included and which items should not be included. Now, it varies depending on the operating system, but the certain items are common for most of the operating system. Now, let's take a look at an example here. Let's just draw a diagram to illustrate the concept. So suppose a process is controlled. So then the operating system going to create a data structure, okay, the PCB. Okay, so now a PCB contains a couple of things. Okay, so for example, the PCB going to contains the CPU state. What's the current CPU state? And a process state. Remember that once the process is created, it could be in the ready state, right? Could be in the ready state or running state or blocked state or whatever. So it could be in a different state. Okay. So these states can be represented using certain numbers like integer or characteristics. So let me actually do this. Instead of writing the value, I can actually put the type for each item. Okay, so this could be integer or characters. Okay, and then where the PCB is located, the memory. Okay, so typically it's going to be a pointers and scheduling information and the files that are opened by this processes and so other resources. Now depend on the operating system. And there are two important information about the process is, so who actually created this process? Okay, sometimes the process is created by another process. So that in that case, the this process should contain the parent item called parent. So it could be a pointer pointing to the parent processes. So where the parent process that actually is pointing to the PCB of the parent processes, Or sometimes if, pointer is not really preferred way. So sometimes some of the operating system use the index. What's the index of the parent process? And then, so this process could create other process. So that means this process is the parent by itself, and it creates some child processes. So it could be at the process may create a whole bunch of child processes. So then it could be the start of linked list. If we store the child processes pointing to the PCB of the child processes using linked list, so then we, that particular actually area could contains the start of the linked list. Okay, so that means it's a linked list, pointing to to another PCB. So these are the PCB of its child processes and so this could be pointing to the parent parent processes, the PCB of the parent process. So you may have a multiple children, but you only have one parent, right? So the open files probably also going to be stored as a linked list. Okay, so it could be a linked list for open files, something like this. So that's also the start of the linked list. Okay, so that's kind of information we need to actually store in the process control block. So this scheduling information could be a set of integers. The other resources could be, also a start of the linked list. That resource probably has a pointer to the actual resources. Okay. So these basically the basic information we need to actually store in the process control block. So initially it's just a blank data structure. Once the process actually start to execute, the CPU start to execute the processes, then these area are going to be filled up. Okay. So some of the information could just a whole bunch of integers. Okay, it's a set of integers. Okay. Some of these are just a linked list. If it's linked list, so the PCB just need to contain the start of the linked list, the first actually starting point. Okay. So each item contains the detailed information about the process control block. So for each process, you need to have the data structure like this. Okay. Okay. Now here is a generic PCB of a process P looks like. Okay. So this is exactly what we did in the previous one, but this one looks much nicer. Now, this table actually lists all the generic PCB fields. So most of the process control block contains. Remember, the first one is called the CPU state. Now, what does CPU state stores? What does first field stores? Now, when P is stopped, remember, in a multi-programming environment, an operating system may actually run multiple processes. Let's say process 1, process 2, 3, Now each process has its own PCB, right? PCB 1, PCB 2, PCB 3, Now the CPU actually switch back and forth among these processes. So CPU first actually execute the instructions for process 1, and then once CPU switch to process 2, then the information every information stored in the CPU for process 1, because it could be like one CPU execute one of the instruction of process 1, and suddenly it's time to switch to the next processes. So now everything stored, the instruction information or the data information stored in this for the process 1, so that the information stored in the CPU for process 1 will be saved in the PCB of process 1, will be saved in PCB 1. Now, where this information will be saved, everything stored in the CPU, that's stored in the CPU state. Okay, so now I'm not going to talk about this in much detail, but if you know the structure of the CPU, now CPU contains a whole bunch of registers. And then there's a control unit, that's the center. And there's an ALU, arithmetic and logical unit. That's the part that they used to do the arithmetic operation, like addition, subtraction, or something like this. And also the CPU may have some special register. One of the special register is called instruction register. The instruction register typically store an instruction. Remember, a process contains a whole bunch of instructions, and the CPU only fetch one instruction into the CPU and decode the instruction and execute the instruction. And where the instruction is going to be stored in CPU, it's stored in an instruction register. So it's a dedicated register. Compare with some generic registers. This instruction register is a register, but only stored instruction. And then it could actually have some other special register, like a program counter. The program counter typically stores the memory address of the next instruction for that process. And the generic register may contain the data this instruction is processing. For example, if the instruction is addition, so then you need to store two values, right? So you can add these two values. It's addition. You perform the addition. These are typically called operands. So these operands should be stored in some of the registers. Okay, these data should be in the CPU during the execution of the process. Okay, now suddenly the CPU say, well, it's time for you to stop, and I'm gonna actually switch to the next processes. Now, before you switch to the next process, the CPU need to save everything inside this CPU to the process control block. Okay, and saved into the CPU state. Now, why? Because CPU say, I'm going to stop you. I'm going to switch to another process, and then the CPU going to actually execute the other processes, and then the CPU going to actually runs another process, and so now later CPU going to come back and start to execute the process 1 again. Now, in that case, once CPU is back to the process 1, then CPU need to continue whatever is when the process 1 was stopped, right? So what CPU operating system going to do? Operating system going to actually check the process 1. Okay, now it will load everything in this process control block 1, the PCB1, back. So everything saved in the CPU state will be reload back to the CPU. Everything saved in the CPU state when the process stopped, and it will be loaded back to the CPU because the CPU wants to continue to execute the process 1. So that's the CPU state. And then the process state, that part is easy to understand. Remember, process state has a ready state, running state, and blocked state, and there might be some other states, right? Okay, but these are the information that will be stored. And the memory basically describes the area of memory assigned to the process. Okay, when a process is running, it may create a various different things. Okay, it may create some other data, temporary data. So these things are not saved in the same location. It could be actually distributed all over the places. So the memory, basically that area, that field, stores the memory information. And then the scheduling information, accounting information. Now people are going to ask why you need accounting information, because it doesn't matter whether you ask the user to pay for the usage of the system, but it did in the past when you have a multiple processes running on a computer system, which is which is located in the computer center. The user wants to use the computer resources, so then the computer center is going to charge the users for the usage. Okay, so every time when the process is created, and then they're going to record how much times you actually used the system. Okay, so they can actually count the resources you use, and they're probably going to charge you for the usage. But most of the time for PC, that information, is probably not that important, because if I own the PC, I'm not going to pay for everything I use for the PC, right? But for some reason, if you use the supercomputer and you want to compute something which is very big, you cannot do this in your PC, and then you can actually just log into the PC and just pay for the usage. Okay, and the open files, every files that this process opens. Okay, and other resources. The now important thing is the parent and the children, right? Remember that the process may be created by another process, so you need to point to the parent. And also the process is going to create its own child process, or created a couple of child processes. So that's going to be stored the information will be stored in the children, in the PCB field called the children. Okay, so that's basically the detailed information about a generic PCB of a process P. Now, in this slide, we're going to talk about how can we organize the PCB, and how does an operating system organizes PCBs. Okay, so remember that when a process is created, then the operating system is going to create a PCB corresponding to this process. So our operating system must allocate and deallocate PCBs efficiently as processes are created and destroyed. So if a process is created, the operating system needs to create a PCB associated with that process. Now, if the process done its job, and you don't want the process to take the resources, right? You don't want the process to occupy the memory space. So you hopefully you want to destroy this process. So then if a process is destroyed or terminated, then you want to make sure that the process control block will be destroyed or eliminated as well to free up the spaces. Now, there are two ways to organize the process control blocks, depend on the operating system. The first one uses the array structure. Okay, the PCBs are marked as free or allocated. So in that array structure, so the operating system need to, allocate certain memory space, and then allocate a whole bunch of structures. Okay, each structure gonna store a PCB. Okay, now, so each block is a fixed size structure. So that structure contains a PCB. Okay, it could contains the PCB information for a process. Let's say PCB1, and then that could be another PCB. Okay. Now this could be empty, and this one could be another process control block associated. I call it PCB10. Okay, instead of 1, 2, 3, it doesn't necessarily follow the same order, and I just use this to record it. So it could be 10, because once the PCB, the first actually structure is actually occupied with PCB1, and once the actual process 1 complete its job, and then the PCB1 will be freed. So that means it will be eliminated, and then this space will be freed. Okay. Now, this approach is very straightforward, right? Okay. So, and the main advantage for this approach is it will eliminate the need for any dynamic memory management. Okay. Now, why is this is good? Because it's fast. So in many cases, if you use a dynamic memory allocation, then the performance actually suffers. The dynamic memory management is good in terms of memory management, because it only creates a memory, a structure in the memory when it's needed. But in this particular case, the array of structure, it doesn't matter whether a process is created or not. So we're going to pre-allocate the memory space for a certain number of, processes. Okay. So initially, even though there's no process created, so these memory space will be allocated, even though each of the space structure is empty, does not contain any PCBs. Okay. So the performance is the advantage of using array of structures. The main drawback is a lot of wasted memory space. Okay, to maintain a sufficient number of PCB slots. So suppose I say, well, the operating system wants to support up to 100 processes, and then the operating system need to allocate 100 structures. Maybe say 0, 1, 2, all the way to 99. Okay. Now that space will be used regardless you have 100 processes or not. Even though you don't have any processes, that space will be allocated. Okay. But they are all available, right? So that's one approach. So if the process is created, the operating system is going to check each of the structure to see, is this structure free or occupied? If it's occupied, then I check the next one. And until I find out, okay, I check the next one until I find out, oh, this particular space is free. There's no process control block stored in here. So then I just say, okay, I'm gonna put the PCB 11 here, and then I mark this space as occupied. Okay. So once the process is actually freed, process is terminated or destroyed, then for example, process 10 is destroyed, then process 10 going to be eliminated, and this space will be marked as available again. Okay. Now this is very simple, but the main drawback is the space. You're going to waste a lot of space. So, but the performance is good. Now the other approach is called using the array of pointers. Okay. So then instead of allocate a whole structure, like this whole structure. So then once the actually structure is occupied, then you're going to put the CPU state, process state, or whatever for each structure, right? Now the array of pointer is different. Now in this case, you're going to create an array. Suppose we're going to support 100 processes. So I just need an array of pointers. Now each of these is small. It just need enough space to store a memory address. Okay. So if I support 100, then the array of pointers, that array is like array of 100 items. Okay. Say this is array number 0, 1, 2, 3, and 99. So if there's no process created, the operating system only allocate this array of pointers. It doesn't take much of the space. Unlike these array of structure, each one gonna take the whole space. So once a process is created, then the operating system can actually create a structure and put a structure somewhere, the PCB structure, and put a structure somewhere, and then mark the memory location and point these to that structure. And then if I create another process, and then I allocate the memory for the other process, okay? And this is a memory allocated for the process 2. It's a PCB2. That's a whole structure. And then I point to the second one to that particular PCB. And so each of these is just a memory address, and sometimes I call that's like an array of pointers. Like this is 0, 1, 2, 3. It's just like an index. Okay. So then allocate to the point. Okay. Now once a process is eliminated, say process 2 is eliminated. Okay, so that means the process control block for process 2, PCB2, should be eliminated, right? There's no need for the process to PCB2 to continue to exist. Now, this is actually a little bit more complicated. So that's the reason why the performance is not so good. Because now you cannot simply eliminate the index, the address. Because if you eliminate the address and then this space is still actually occupied, but then you lost the pointer. So this is called a dangling space. This is going to be causing some memory leak. So then what you need to do is you first need to destroy this data structure, and then you free up this pointer. Okay, you need to destroy them. Don't forget to destroy it. You cannot simply destroy the address in the array. Okay, don't destroy the pointer first. You have to destroy the object this pointer is pointing to, and then before you destroy the pointer. So that's why the performance suffers. The good thing is once a process completes its job, then that process no longer take the space. Unlike the array structure, even though the process is destroyed, and then you only free up that space, but that space still takes that much memory. So this structure still takes that much memory space. Okay, so it doesn't change. But this one really actually gonna free up the memory space. That's the main differences. But still, the array of pointers are very actually expensive. It requires a dynamically allocate the PCB, and the performance is going to be very bad. Okay. Now, in the implementation of the PCB, it requires a data structure. In certain places, it may require the linked list. Now, one of the example is, let's see, if you still remember, just recall any PCB. Let's draw a PCB. Remember, the PCB has various different fields, like a CPU state or the process state. And then remember, if you still recall, the last two, one is the parent, and the other one is children, right? So many times the parent is the pointing to the parent, and then the children basically all contains all the pointers pointing to the child processes. Okay, now in that case, it requires some of the linked list implementation. Now, linked list has one advantage. So that means the memory going to be allocated only when needed. When you want to create a memory space to allocate the data, and then you create the data structure, allocate the memory space, and then just create a structure and put in the memory. And when it's not needed, then you can destroy these, the structure. Okay, so you're going to free up the memory. However, this is also the drawback for the linked list. Because linked list requires dynamic memory management, which is very costly. When I say costly, it's just mostly costly for the performance. The performance is going to suffer. So instead of the operating system, like a Linux operating system, they just try to pioneer an approach to eliminate these overhead. They try to avoid the linked list. Okay, now let's take a look at the example. Now suppose I have a couple of processes. Now first the process 0. Okay. Now process 0 has a couple of child process. So that information is going to be put in the children field, right? In the PCB. Remember. Now okay, that's probably the ID. Remember, each process should have an ID. So now process 2 also creates its own child process. So, and mostly if the process 0 has no parent, so that means process 0 probably was created during the system initialization. So it is, sometimes this is called a root process. So there's no parent, but the process 1 going to create a child process. Now typically using linked list, the process 0 going to create a linked list here. Okay, so process 0 has 3 child processes, 1, 2, 3. So you're going to create a linked list for 3. Now each, that's pretty much the address, right? Pointing to process 1, that's the memory address pointing to here, pointing here. And now this also contains the link to the next one, Okay, now I call this, pointer to its children. Okay, and also in order to actually manage these easily, each child process, remember, so you're going to have a PCB 0, right? And then you have a PCB 1, PCB 2, PCB. Remember, it doesn't matter whether this process is is a parent process or child process, there's always a PCB associated with and the PCB4. So this child process also contains a field called a parent. So basically, this parent is just the pointer to the parent process. So then it's pointing back in the parent process, right? To the parent process. And this one pointing to the parent process. And this one pointing to the parent process, right? Now, same thing. If 2 actually created something, so process 2 has also created its own linked list. And this point, process 2 has only one child process 4. So then you're going to have a memory address in the linked list and then pointing to its child, right? And this child process in the PCB4, the child process, the process 4, also has a pointer pointing to its parent, right? Okay. I think that's the structure with the current setting. If you have a parents and you have a children, and then if process 2 wants to create another process, I say process 5, and you're going to create the process control block 5, right? So then you need to set up the values for the parent and for the children for that in that PCB, so in the PCB. Okay. So let me actually change the color, so make it much better. So let's say so this process control block 5 gonna contains its parent and its children. Now so far parent 5 has no children, but it has a parent, so it points to the parent. Okay, so just I fill that information in that parent, and then this parent also gonna create another index in the linked list and point to the child. Okay, so the parent also gonna point to the child. So this gonna update the PCB2, right? So for the PCB2, they will update this field, okay, to include additional child, which is process 5. So that's the linked list implementation. Okay, now this is kind of costly because every time when you create something, you're going to create a pointer and a point to the child and then a pointer back to the parent. Okay, now the Linux operating system tried to implement another approach. Instead of a separate linked list anchored in the parent PCB, the links are distributed over the child PCBs such that they each point to the immediate younger siblings and immediate older siblings, and then organize original 2 fields, parent and the children, in the PCB of the process P are replaced by 4 new field. Now you can probably figure out, oh, why this is simpler, why this is better. Instead of using the pointing to the child, point to the parent, now you have 4 fields. Okay, parent, first child, and then the parent only points to the first child. The parent does not point to any child. So in this case, the parent point to let's see, the parent point to the first child, and also the parent point to the second child and point to the third child. If the parent has 9 child process, the parent is going to have 9 pointers, right? Pointed to 9 is child. But in this implementation, the parent does not point to every child. Okay, only point to the first child. Okay, and then there's this implementation, there's no relationship between the children's, right? Parent, process 1, process 2, process 3, they are pretty much isolated. So there's no relationship. Okay, so in this new implementation, there's a links between the younger the siblings. Okay, so process 1, 2, 3, these three processes are siblings, so they actually going to point to each other. Okay, using the younger sibling and the older sibling. Okay, so now what's so good about this implementation? You're probably still going to wonder, right? Now let's talk about this a little bit later. So the main thing is that this implementation requires no dynamic memory management. Okay, that's the one that requires a lot of actually time to implement. So the performance is going to suffer. But if this new implementation requires no dynamic memory management, the performance is going to be improved. Okay, let's see. Okay, so let's look at the Linux operating systems approach using the using 4 pointers instead of the linked list approach. Okay, now, so this is actually the one we using the linked list. You know, we did it in the previous slide, but I just summarize over here. This is the diagram I just got from the iBooks, which looks much nicer than the one I just drawn. Okay, so now using the new approach, so assume that we still have these 5 processes. Okay, so you have a process 0, process 1, 2, 3, 4. Okay, now using this approach, now we have each child process gonna point to the parent. So this is still the same. Okay, there's no change on this. However, we avoid these linked list here. Okay, now for the parent process, it has a pointer to the first child. Okay, there's a point, but there's no other points. Okay, so there's no such a linked list that contains the index, the address, and then each pointing to its children. But in this case, only pointed to the first one. The first child process that was created by the process 0, process 1, will have the pointer to point to that process 1. But not once the second process 2 was created by process 0, and then there's no point on this. Instead, it used the it's called a sibling, the pointer that point to each other. These are called a sibling point. So this is actually the first child to create. So this is actually the older. Okay, this is the older child. This is a younger. So this is the older sibling. So then you have a pointer pointing to the younger sibling, and then the younger sibling pointed process 2 pointed to the older sibling. Okay, so they actually pointed to each other. Process 1 and process 2, they pointed to each other. Okay, now when process 3 is created by process 0, okay, so then you only create 2 pointers, younger sibling and the older sibling. That's it. Okay, so the process 0 can access any of the children through the older child, and then through the younger sibling and the older sibling through this pointer, and then you can point it to any other children. Now, same thing with the process 4. And so process 4 is created by process 2, right? So the process 4 going to have a pointer pointing to its parent. And the process 2 also has a pointer pointing to its child. Okay? That's it. Now, if you have more processes created, process 5. Let me actually change the color. Okay, so I have a process 5 created. Okay, now in that case, of course, process 5 is created by process 2. So process 2 is the parent process. So you still need to point it to the parent process, that's for sure. But the parent process doesn't have a pointer pointing back to the child process because it doesn't want to create like a linked list anyway, right? So then instead, you create 2 points. That's the parent, the child. That's a older child for process 2, and this is younger. Okay, so then the younger child pointing to the older child. Okay, so that's basically the approach. Use this. Now again, what we can say is, what's the advantage of using these approach? Then the main point is this implementation requires no dynamic memory management. Okay, let's study it further. Okay, let's continue with that example, and let's explain why there's no need for the dynamic memory management. Okay, so that's the implementation without linked lists. So again, we have 5 processes. Process 0, process 1, 2, 3, and 4. We have 5 processes. And then process 0 is the parent process. And the process 1, 2, 3 are the child processes for process 0. And the process 4 is the child process for process 2. Okay. Now in that case, all we need to do is we need to actually complete the array to show the relationship. Okay, so let's do this. So we can draw this table of array. Each column represent process. Okay, and then so let's see something, and then we have 4 pointers. Parent point, younger sibling, the older sibling, and that's process 0, 1, 2, 3, 4. Okay. So let's see. Here we see the hierarchical structure, the child and the parent-child hierarchy, right? Now let's reflect on this table in array. Okay, so we can actually do this for process 0. Okay, does the process 0 has a parent? Looks like in this diagram, definitely there's no parent, but we don't know. Maybe this is just a part of the parent-children hierarchy, right? So let's just put the question mark. If P, process 0, is the root process, the very first process, then there's no parent. So you can put a dash here. But here, I just put the question mark saying, okay, I don't know whether there's a parent or not. Put a question mark. And then, does the process 0 has child process? Yes. There's a 1 child process, right? So it just pointed to it's the 1. Okay. Now the process 0 has a sibling? No.
Doesn't look like process 0 has a sibling at this moment. So we put a dash here. Okay. Now we just fill up the information for process 0. And then now let's take a look at the process 1. Now the process 1 has a parent? Yes. Process 1 has a parent. It's 0. Does the process 1 has a child? Any child? No, doesn't look like. So we just put the dash here. Does the process 1 has a sibling? Yes, 2. So it actually pointing to a younger sibling. Does the process has an older sibling? Looks like the process 1 is the oldest one, right? It's the first child for process 0. So then there's no older sibling. Okay, so that's the table for process 1. Now let's just fill in the process 2 information. Now does the process 2 has parent? Yes, 0. Because process 2 also pointed to the parent, so that point is pointing to 0. Now, does the process 2 have a child? Yes. Which one is child? 4. Now remember, at this moment, the process 5 hasn't been created yet, right? So we only have 0, 1, 2, 3, 4. And then we're going to talk about how can we update this array, the table, once we actually add another process, another child for process 2. Okay, so at this moment, process 2 has child 4, which is point 4, and then does the process 4 has a sibling? Process 2 has a sibling? Yes, the sibling is 3. Okay, now does the process 2 has an older sibling? Yes, because 2 is not the oldest one. 2 is younger than process 1. Process 2 is younger than process 1. So it's 2. Okay. So it's a 0, 3. Oh, I'm sorry. That's not 2, it's 1. 2 is the process itself. So it's so the child is 4, younger sibling is 3, and the younger sibling is 3, and the older sibling is 1. Okay. Now let's fill the information for process 3. So the process 3 has a parent, right? And the process 3 has child? No. Process 3 has a younger sibling? No. Looks like the process 3 is the youngest. So no. Older sibling? Yes, 2. 2 is the older sibling, right? That's it. And then let's take a look at the process 4, which is the child of process 2. So then, what's the parent? 2, right? Does it has a child? No. So I just put dash. Does it has a younger sibling? Now remember, process 5 hasn't been created yet. So at this moment, 4 has no younger sibling. Okay. Don't look at this one. Don't look at this diagram, but this diagram is not complete yet. It's just actually 0, 1, 2, 3, 4. Okay. And then no, for the older sibling, because 4 is the first child of process 2. Okay, so it's supposed to be the older one, the oldest one. Okay, so that's the information we need to fill at this moment. So we don't need to create any dynamic, link manager. We need to require a dynamic link manager. All you need to do is to fill up the table. Now let's take a look at the next step. Now suppose we add another process, and this process 5 is created by process 2. So 4 and 5 are the children of process 2, right? So then, based on this approach, so you don't have to actually create a pointer from process 2 to 5, because process 2 only pointed to its oldest child. But this child, process 5, should point to the parent. Okay, and then you're going to create a pointer between the siblings. So the 4 going to point to 5, and this is the 5 is a younger sibling, and then 5 pointed back to 4, which is the older sibling. Okay. Now, once we add a process 5, then we need to update the table, right? So we're going to update the table to include another process 5. So now what the information we need to change? Okay, we don't just simply add information for 5. We also need to update the information in other processes. Okay, we need to check which information we need to add and which information we need to change. So once we add a 5, then the first one for 5, we need to fill out the 5. So does the process 5 has a parent? Yes, definitely. 2 is the parent, right? So I use different color here. Now, does the process 5 has a child? No, nothing, right? And does the 5 has a younger sibling? So you look at the right, looks like a 5 is the last one. So there's no younger sibling. But does the 5 has an older sibling? Yes, it has an older sibling. Okay, so it's 4. Now, what the other information you need to change? Because you have a process 5 created, which is another child for process 2. So initially, process 4 was the only child, but now process 4 has a younger sibling now, right? So now you need to create updated information for process 4. Now process 4, the younger sibling, it was actually empty, but now you need to change. It's not dash anymore. The younger sibling can be 5. So we need to update that information. Now, what the other information you need to update? The older sibling? No older sibling, because that's still 4 is the oldest one. And the parent doesn't change for the parent. The parent, both parent, the parent for both 4 and 5 are 2, right? So nothing else need to change. So that's the table we need to change. You only need to change add these item, but only change this item, because now the process 4 has a younger sibling. Okay, so all you need to do is update the table. So that's good. So we don't have to do actually adding any linked list and create a pointer, the address to the next one and the next one. So that's very costly.
Okay, so before we wrap up the section 2.3, let's actually talk about how an operating system manages the PCBs. Remember, once a process is created, a PCB will be created as well. Now, how does an operating system manage the PCB? So the operating system maintains all PCBs organized on various different lists. Okay, so let's see. Suppose we have a computer system with various different resources. I say resource 1, resource 2, now if you think about the CPU, you take CPU as a resource. It's also CPU is a resource, memory is a resource, a USB port is a resource, and there's so various different computer components, and each of these resources, and our process need to have some resource to execute. Now, for each of the resources, there's a waiting list. Okay, so a waiting list is associated with every resource and contains all processes blocked on that resource. So if a process, say it's created, but process needed that particular resource to run, so the process going to be on the waiting list for resource 1, and another process going to be on the waiting list for the resource. Okay, so then each PCB going to be on the waiting list for that particular resource. Now that's a waiting list for this particular resource. Now another resource 2 has a list, right? Which has a couple of which has a PCB, another PCB, all the processes that the PCBs of the processes waiting for that resource going to be on this waiting list. This is another waiting list. Okay, so this is the waiting list 1, waiting list 2, and then each resource going to have a waiting list. Maybe no process used that particular resource N, and then the waiting list is empty. Okay. Now CPU, if you treat CPU as a resource, and then there's a whole bunch of processes. They don't need other resources, or they already got the other resources, so they are ready. So they're in the ready state. Okay, so they're waiting for the CPU. Okay, so then they're waiting for the CPU. I'm not going to draw this here because this waiting list is a little bit more complicated than the other, the waiting list of the other resources. So that's why sometimes the waiting list for CPU, it has another name. It's called a ready list. Okay, RL. Now let's draw the ready list separately. So let's say a ready list consisting of the processes, the PCBs associated with different priorities. Okay, remember all the processes, each process has its own priority. Remember the hierarchical structure we talked about? You have a root process, you have a level 0 process, level 1 process, level 2 process, and these processes have different priority. Okay, what does that mean? So that means some of the process has higher priority than the others. So once the CPU is available, then the operating system gonna favor the higher priority than the lower priority processes. Okay, so that's why I'm not gonna actually use that similar waiting list for CPU. So CPU, the waiting list for CPU is kind of special. It's gonna look like this. So you have some priority 0, priority 1, priority 2. So you have various different priorities. So priority 0, 1, 2, and let's say 2, 3, 4, 5. Let's say 5, 6, 7, 8, 9, and then the highest priority is priority N. Okay. So it's consistent. So the ready list, also the waiting list for CPU, is a ready list. The ready list consists of priorities 0 through N, containing process at the level, different levels. Okay. So so suppose we have a couple of processes, like these are the processes pointing to the pointers to the PCBs that's at the level the 0. And then we have a level 5. You have a whole bunch of processes over here point to the CPU. And also we have a level 7. There's a process actually at the level 7. And the level 7 has a higher priority than the others. Now at this moment, suppose level 7 is the highest priority process. So the PCB associated with the level 7 has a higher priority than the processes associated with level 5 or level 0. So suppose this one is running. Okay, this process is running at the level 7. Okay. So while this process at the level 7 is running, and then a new process is coming. It's positioned at the level 5, suppose. Okay, and then you can actually start using the interrupt to interrupt whatever is doing right now, with which the CPU is running this process at the level 7, and the CPU stopped and the process the interrupt. The interrupt tell the CPU, say, okay, we have a new process coming, but the new process has a level 5. So the operating system think, oh, it's level 5, it's still lower than 7. So once the interrupt is completed, and the process is going to actually, and the CPU going to go back to the level 7 and continue to run the process at the level 7. Okay, that's what it is doing. So now when a new process is created and a new process is entered at the priority above 7, let's say a new process is coming here, okay, which is a much higher than 7. And then the current running process is going to be stopped, and then the operating system is going to put the current running process into as a ready state and start to run this one. So this is going to be put back to as a ready, okay, in the ready state. So that means the PCB of this process is going to be, the process state is going to be set to ready, not running anymore. Remember, there's only one process should be in the running state for a system with one CPU. Even if you use the time sharing to share the CPU and with a multiple processes running on the same one CPU, but only one process is going to be in the running state. Okay, so this is the situation. So the ready state, ready list is a very important one. That these are all the process that they're waiting for, waiting for the CPU, and only one is running.
Okay, now let's actually talk about section 2.4, operations on processes. Remember that modern computer systems supports many processes. So you have multiple processes running concurrently. Okay, however, all the processes are not created equal. Okay, so if you talk about all the processes in a computer system, you're going to actually see a process creation hierarchy, which is, if we use a graphic representation, you can see a kind of a tree structure. So for this, now let's get into the details of this. Okay, let's see how these hierarchical structure going to be created. So initially, when you turn on the computer system, the operating system is going to be loaded, and then the first process will be created, and that process is called a root process. Okay, that's called a root process. And then, so the root process then going to create some other processes, some processes that run in the operating system. Okay, I call it OS1, I call it OS2, or you can have many other. And the root process is actually many times it's at the level 0. And then you have a level 1, right? And so this is actually the, so there's only one at the level 0. That's only the root. Okay, and then you have a multiple level 1. And the one of the operating system processes become the highest ancestor of all user processes. Now, in most of the operating system, the user process will be created after the operating system is loaded. And then before the user process is created, the operating system is going to create a process. That process, many times we call these the root process. That's called init. Okay. One of the operating system, the Unix, which was the operating system used in like 15 years ago. Okay, it was a very popular operating system, and the Unix created the init. Now the Linux now also used a similar structure as Unix, so you're going to create a process called init, and that init is the parent of all the user processes. Okay, the init is at the level 0, level 1. Sorry. Okay, then let's actually use different color. Let's see. So if a user process is created, so whenever a new user logs in, a new user process is created. And then that's the user process is created at the level 2. Okay, so then, so here's, you're going to see a user process 1, user process 2, 3, and all the user process has one parent. That's it. Okay, that's the init. Let's say user n. Let's say user n. Okay, so now each user process can create its own child processes. Okay, to perform various tasks. For example, the user 2 can create a child processes. Let's actually change the color again so we can make it much better. So the user actually can create a child process. Say, for example, in Microsoft Windows operating system, you can create a program that running the browser. We say Edge. Okay, Edge is the one, and then you can also create another process like if you use the applications like Skype, and then you can create a whole bunch of different user processes. Okay, and then so you can create another one. Okay, I don't even bother to put the name here. And then this user process, that these are all at the level 3. Now each child process of user 2 can also create another level of user processes. Okay, let me try another color to show the difference. Okay, let's see what's the other user process that I can use. Okay, I use this different color. So I can create another user process. Another user process. Now this is at the level 4. Okay, I just say compute 1, compute 2. So I don't even know how to name this. Okay, now that's the the hierarchic structure. Now, kind of easy, right? So now you're gonna see an operating system running so many processes: root, OS1, OS2, init, user 1, user 2, user n. So these are different processes. As I say, that these processes are running at a different level, and typically the smaller, the top levels are mostly the processes running the operating system. Okay. Now the bottom level is mostly user processes. Okay. The top level process may mostly running at the using privileged instructions, something like this, and the users use the user instructions running in the user mode, and these are mostly running at the kernel mode, if you still remember the chapter 1 topics. Now here's the issue we need to think about. Okay, because for some reason a process will not run forever. It has its life cycle. So if the process is created, then you create the process, you create the process control block, and you create all these data shares. So each of the process here going to have its own process control block. So the process is actually running. Now, what about if somehow a process is terminated, or a process could be terminated by itself, or could be destroyed by some other process because you're not doing the right thing. So the other process, the process in the operating system want to eliminate that particular process. Let's say if this process is destroyed, what's going to happen? What about the child process? Now, so what? All the children gonna lose their parent. Okay. Now, this is not gonna happen in the operating system. Don't worry about this. Okay, but we need to actually discuss a different scenario. Okay. Now, depend on the operating system. Certain operating system, for example, like an operating system, Unix operating system, if one of the processes is destroyed, now all the child processes going to be repointed to the init. Okay, let me change the color again. Just change back to the green, the red color. So let's say this process is destroyed. Okay, it's not there anymore. Now, so the edge, it used to point to the user process 2, but now it's going to be rerouted to the init, and also the Skype, and also whatever this process is going to be rerouted to the init. So now the init becomes the parent of all these processes. That's what the operating system like a Unix do. Now, there's some other operating systems. Their actions come kind of different. Okay, so let's say, so this is Unix. The Unix is going to reroute all the child process to the init. Now, some other operating system, they're very direct. Okay, so if let's say, let me actually move that one. Okay, now if the parent is destroyed, okay, now so the parent is gone. Now the operating system is not going to actually leave all these process like orphan. So that's not the way that the operating system can do. What the operating system is going to do is, well, instead of actually reroute, these, find a new parent, operating system is going to simply destroy all the child processes. Okay. Okay, destroy everything. Okay. So that's, the action by some other processes. Okay. So, oh no, I'm sorry. That's the action by other operating system. So the other operating system choose destroy the processes as well as all the processes descendant. Okay. So when the parent dies, all the children are gonna die. Kind of rude, right? But that's the other implementation. So you have two type of implementation. Like a Unix, it's kind of nice that they can find a new parent for them. But the other operating system can simply, if the parent died, every child can die as well.
Okay, so that's the process creation hierarchy we just discussed. Now this diagram is much nicer than the one I just drew. Okay, in the next two slides, we're going to talk about the process creation and destructions. Okay, when the current running process initiates the creation of child process, the operating system executes the creation process function. Now that function is called create. Okay, so the create process function first allocate the new PCB. Remember the PCB, the process control block, is the data structure that the operating system is going to create when a process is created. And then the operating system is going to fill the PCB entities, the fields, with initial values, and also the links to the PCB to other data structure in the system. So, so that's the thing. So a new process is allocated, PCB is allocated. The PCB uniquely identify pointer or the array index P. So that's the one. And then the field, like a CPU state, memory, scheduling informations. Remember all these different fields in the PCB gonna be filled using the initial values. Okay. Now, so most of the operating systems use the C language. So the create function gonna look like this. So let's say you're gonna create the function called, you're going to run the function called create. So you're going to have some initial values like the parameters, like a state, memory. So these initial parameters are going to eventually fill in various different area in the PCBs. Okay, so then P, that's the allocate. So that's the way you're going to create. So you use the allocate to allocate the P, and then P dot CPU state. So P is actually the data structure you're going to allocate in the memory. So P dot CPU state, that's the first field. Then the state 0. So this is actually initial state for the CPU state. And then the other state is process. Let's say memory, P dot memory. So this is going to be the initial value. That's when you call the function create. So there are lots of different things, and including p dot parent. Okay. Now, if this is the initial function that create that process that's created, the parent is going to be the self. So there's no actually parent. And then you have probably insert some other process into, because the self, it's self dot children. And eventually the last one, the last actually line, last actually statement are going to be basically insert the process, the P, into the ready list. So make sure, okay, this process is ready. So waiting in the ready list to fight for the CPU with the other processes. So this is actually how, the process is going to be created. The next one is the process destruction. A process P can be destroyed or terminated by the parent process by calling the function. That function is called destroy. Destroy. So the destroy process function destroys the process by freeing the PCB data. Remember the process creation, you just create the field and fill the data for in each field. But the destruction is basically doing the opposite. Big destruction is doing the opposite, and then it just remove any references to the PCB from the systems. Okay, so the destroy function perform basically the following function. after the destroy function is called, so let's say that this is a destroy. So basically, you're gonna for all C the in P children, you basically destroy C. Okay, so you basically destroy all the children, and then remove P from the ready ready list, because the process is going to be destroyed. It will no longer wait for the CPU anymore. So remove P from the ready list, or if this process is on the waiting list for any resources, and remove from the resources. Okay, remove P from parent list. If this is actually created by another process, the parent process, you have to remove this process from the parent's list of children. Okay, so all this is doing the cleanup. Release P dot memory. So whatever the memory is just used, you need to release it, and close se or P dot open files. The process may open a couple of files, and then if the process is destroyed, you need to close all the files, open files, and then the last step is you're gonna deallocate. You're gonna deallocate PCB. Okay. Now after you destroy it, and then you're gonna call a function called a scheduler to schedule the next operation. Maybe the CPU gonna actually run the other processes, so the follow-up actions. That's basically the steps for process destruction. Now that's all for section 2.4. That's the end of the this video file. Thank you.